Hello student, welcome to lecture series on Fourier transformation. Already I have uploaded some definition and basics results rely on Fourier transformation. So if you are interested to see this video, check in my playlist. In my today's video, I'm going to explain to you all one of the very much important example that asked every year in Sppu question paper. Okay, so that one is here. Find Fourier transformation. Okay, that one is the example. So in my today's video, I'm gonna explain to you all this complete example. How can we solve? Okay, so let's get dive into our today's lecture. We'll see how the solution it look like. So here in our example, we have given f of x. Okay, f of x as a piecewise function. We have f of x as a piecewise function. So we need to understand what actually the meaning of a piecewise function, because the piecewise function defined for different values, okay, under some intervals. Now see that I'm going to explain that interval over here. Okay, so we have f of x as 1 and 0. F of x as 1 and 0. That means f of x is 1 whenever we have modulus of x which is smaller than 1. Okay, modulus of x is smaller than 1, and when f of x is a 0, we take all the value for modulus of x which is bigger than 1. Okay, now see that we have the two values for x, which is a mod x smaller than 1 and mod x bigger than 1. Okay, yes, we have to find out the Fourier transformation for this function. Okay, and then we have to evaluate sin x upon x. Okay, 0 to infinity sin x upon x. So we do that evaluation later on. First of all, we go for finding the Fourier transformation. Okay, now say that for finding the Fourier transformation, okay, Fourier transformation for function, how can we write Fourier transformation? Fourier transformation of function, any function you consider. I consider Fourier transformation of f of x. Okay, we write capital F of s. Okay, f of s, capital F defined as a Fourier transformation, okay, on s. Okay, so we write capital F of s, which is equal to minus infinity to plus infinity, small f of x. Okay, small f of x e raised to I times s x dx. Okay, so this one is our Fourier transformation here. Okay, formula for Fourier transformation. Using this formula, we have to evaluate a Fourier transformation for this piecewise function. Okay, for this piecewise function. So what we do in such a case, first of all, we go for understanding these intervals. Okay, these intervals are very much important here. Okay, now let me explain. For modulus of x which is smaller than 1, we get the all function as f of x 1. Okay, now let me x how it is 1 coming. Okay, modulus of x is smaller than 1. Okay, that means x has a positive negative value but which is smaller than 1 whenever we take that x out of the modulus. Okay, we know that the use of modulus, it absorbs negative signs. So whenever we take outside that x from modulus, we get the plus x and a minus x. Okay, when we take x outside from this modulus, okay, then we get plus x and minus x. So plus x which is smaller than 1 and minus x is also smaller than, I'm explaining for this one only. Okay, for modulus x smaller than 1, I'm explaining this one. Okay, so mod x smaller than 1 means positive x it is smaller than 1 and a minus of x it is also smaller than 1. Okay, yes, so we can see that all the value for x which is smaller than 1, okay, which is smaller than 1, but we cannot define any value over here, minus x as it is here. Okay, so try to remove that negative sign. So what I'm going to do here, I'm going to multiply negative sign to the both side. Okay, so minus x into minus x, it become positive x. Okay, yes, so that's strictly less. Okay, less equal, when we multiply negative, so it become greater. Okay, this one is a lesser than, when we multiply negative sign to the both side, we get the greater than. Okay, and minus 1 it is here. So I write this step as a minus x less than 1 as a x greater than minus 1. Okay, so I got these two value for x. Okay, these two value for x where f of x gives us the value 1. Okay, I hope you all have understood these two different values. Okay, so let me draw this value in our real line. Okay, then it will be visible for us. Okay, so now say that it is a 0 here, it is a -1 here, okay, it is 1 here, it is 2, it is -2, okay, and so on. Okay, this one is our interval. Okay, this one is our interval, -2, -1, 0, 1, 2, and so on. Okay, these are the infinitely many terms here. Okay, as we have Fourier -infinity to +infinity, so we have to take here as a -infinity, here it is the +infinity. Okay, yes. Now see that when we are going to define f of x as 1, when x is smaller than 1, now see that smaller than 1 means the value which is from here, this side. Okay, that means all the value from here. Smaller than 1 means all x contain the value which is smaller than 1 means it is from this side. Okay, yes. And the next side value, all the x which is bigger than -1. Okay, that means this sign make a face, wherever it make a face, now that value goes to bigger. Okay, so that greater than value, greater than sign which makes the face on our x. Okay, so the x it is bigger here. Okay, so obviously all the x which is bigger than -1, so we go from here to this side. Okay, this one. So whenever we have f of x which is equal to 1, whenever we have f of x which is equal to 1, we consider x as a -1, dash dash dash, all points here, x as a 0, x as a 1. Okay, so all the value for 1 to -1, between 1 to -1, f of x gives us the value 1. Okay, try to understand the meaning for this piecewise function, guys. It is one of the easier. Once you understand this one, later part is easier. Okay, so now see that mod x is smaller than 1, that means our f of x gives us the value 1. So mod x smaller than 1 means our f of x lies between 1 and -1, as I explained here. Okay, yes. So for all the value between -1 to 1, we consider f of x is a 1 here. Okay, yes. Now what about for the another f of x is a 0? So we are going to expand this mod x bigger than 1. Okay, yes. So I'm going to explain for the second step here. Okay, now see that carefully. Whenever f of x is a 0, whenever f of x is a 0, what is the x? Mod x bigger than 1, mod x greater than 1. Okay, yes. So I'm going to explain that modulus. Okay, mod x greater than 1. So it gives us -x also bigger than 1 and +x also bigger than 1. Okay, that modulus means it contain negative x and it contain positive x also. Okay, so -x bigger than 1 and +x bigger than 1. So it comes sense from this step. Okay, that x is greater than 1, it is a sense here. Okay, so we get the some sense that x goes to 1, 2, 3 and so many values. Okay, yes. But -x greater than 1, it won't be visible all values. Okay, so multiply negative sign to the both side, -x into x, which gives us the value x. That greater than goes to the less than when we multiply sign, and x is smaller than -1. Now see that x, all the value for x which is a smaller than 1, smaller than -1, and all the value for x which is a bigger than 1. Okay, we consider f of x as a 0. Now see that x is a smaller than -1. Now see that -1 smaller, that means all the value it goes here. Okay, to -infinity. All the value we have here smaller than -1, x is smaller than -1, we consider f of x is a 0 here. Okay, yes, I hope you all have understood. Okay, and whenever we have f of x bigger than 1, okay, that means all the value for x which is a bigger than 1 means it goes here, then we consider f of x as a 0. Okay, yes, I hope you all have understood. Okay, this is my this is a given piecewise function, how I explained here. Okay, yes, so whenever we have 1 and 0 value, okay, for our mod x less than 1 and mod x greater than 1. Okay, so all the values I explained here, I hope you all have understood. Okay, using these values I'm going to expand this integration. What I'm going to do, I'm going to expand -infinity to infinity using all these values here. Okay, now see that how many interval we found here. -infinity to -1, it is a f of x for 0 which is equal to, we got the -infinity to -1. Next -1 to 1, and later on 1 to infinity. Okay, let me expand this Fourier transformation for these 3 different intervals. Okay, so f of s, that Fourier transformation on s can be written as -infinity. Okay, minus infinity to minus 1, okay, f of x e raised to isx dx, f of x e raised to isx dx, okay, plus. Now I'm going to expand next interval, okay, minus infinity to minus 1. So minus 1 to 1. Next interval minus 1 to 1. Okay, what we have, f of x e raised to isx dx, f of x e raised to isx dx, okay. Yes, this one is our next interval, minus 1 to 1, okay. Then third interval, okay, 1 to infinity, okay, 1 to infinity, f of x e raised to isx dx, okay. Yes, these are the three interval we have here, okay, minus infinity to minus 1, minus 1 to 1, and 1 to infinity, okay. We have these three intervals. Yes, so for all these three intervals I am going to define f of x for three intervals, okay. Now see that capital F of s, capital F of s I am going to write here, capital F of s. Yes, now see, minus infinity to minus 1, minus infinity to minus 1, whenever we have the value, any value, whenever in this interval, we write f of x as 0, okay. That means this whole term, it goes to 0. F of x is a 0, that means the entire term goes to 0, okay. Plus 1 to minus 1, whenever we have minus 1 to 1 interval, minus 1 to 1 interval, okay. So in this interval, okay, so minus 1 to 1, in this interval we take f of x as a 1, okay, f of x as a 1, interval between minus 1 to 1, we take f of x as 1, because all this value gives us the value f of x 1, okay. So I consider f of x is 1 e raised to I times s x, okay, e raised to I s x dx, okay, plus. Now see that 1 to infinity, all the values for 1 to infinity, our f of x gives us the value 0. So that means this f of x gives us the value 0. So if f of x is a 0, that means entire integration goes to 0, okay. So what we left here with the value 1 to minus 1, okay, e raised to I s x dx, okay. This one is our given f of s, okay. Our given f of x is a minus 1 to 1 e raised to isx dx here, okay. So this integration we have to solve. Now see that how I have reduced my integral over here, okay. How I reduce? I just converted into the three different intervals. Then wherever function gives us the value 0, I replace that one here, and the remaining integration we have it here, okay. Yes, so we have to find out this integral with the limit minus 1 to 1, okay. So let's go for finding f of s, okay. F of s is equal to e raised to isx. What is the integration of e raised to x, which is e raised to x itself, e raised to isx itself, upon differentiation of isx, which is is here, okay, and which has a limit, upper limit and lower limit 1 to minus 1, okay. Yes, I hope you all have understood this integration, okay. Not that difficult. So now see that how I'm going to write this step here. Replace x as a 1, as we are taking differentiation with respect to x, okay. So replace x as a 1 and then minus 1, okay, e raised to I times yes, okay, x is a 1 upon, okay, e raised to, I replace x1 upon is, okay, here is, again minus e raised to is of minus x, okay, e raised to minus is, then by is, okay. This one is our substitution. I hope you all have understood. First of all, we go for substitution of 1 into entire term here, which gives us this value, okay. Yes, and after this we replace minus 1 instead of x here, okay. So minus 1, it uses the minus, okay, and we take subtraction between the terms, okay. As we have a similar denominator, take it once, okay, and take it outside. So 1 upon is, okay, 1 upon is. I don't take I common, just take is common from here, okay. So under bracket we left here is minus e raised to minus is, okay, e raised to is minus e raised to minus is, okay. Let me write on the next step here, okay. I will write here downside, so it is way clear for us, okay. So yes, take denominator common here, so we 1 upon yes, it is outside, okay. Yes, under bracket we left here e raised to is minus e raised to minus is, okay, divided by, okay. So divided by I it is here, Okay, this one is the next step I written here, f for capital F of s. Okay, so we want the Fourier transformation. Okay, yes. So what we do in our next step, we know that one of the standard result, okay, one of the standard result that we learn in our previous lectures also. Okay, so let me write that result here. So we can write sine theta. What is the value for sine theta? Okay, so already you all have learned these values. Okay, sine theta. So why sine theta? It is the value for one of the Fourier transform here. So I will explain in our next part. Okay, yes. So sine theta can be written as e raised to I theta, okay, minus e raised to minus I theta divided by 2 times I. Okay, this one is the value for sine theta. We are going to apply it here. Okay, this is the standard result. You all need to remember e raised to I theta minus e raised to minus I theta divided by 2 times I. Okay, and a cos theta, there is also one of the value which is a cos theta. Similar we learn in our hyperbolic function, e raised to ix plus e raised to minus ix by 2. Okay, so these are the similar like a hyperbolic function, but as we are taking under trigonometric, so the values are changing here. Okay, sine theta which is e raised to I theta minus e raised to minus I theta by 2i, and a cos theta can be written as e raised to I theta plus e raised to I theta plus e raised to minus I theta, okay, by 2. So see here guys, I am going to apply this sine theta result over here. Okay, as we have e raised to I theta minus e raised to minus I theta by I. Okay, but as we don't have denominator 2 now, so multiply by 2 and divided by 2. Okay, so we are going to multiply and divide with the 2, so we'll get the entire term here. Okay, now see that this is the term in the form of s, this is the term in the form of theta. Try to replace the values. Okay, so I'm going to write sine theta as a sine s. Instead of a sine theta, I'm going to write s. Okay, so e raised to I times s minus e raised to minus I times s divided by 2 times I. Okay, now see that carefully. Instead of a theta, I replace s only here. Okay, so it will be the equivalent to this step. Okay, e raised to is minus e raised to minus is by 2i. Okay, e raised to is minus e raised to minus is by 2i. Okay, this one is the value for sine s. Okay, replace that sine s. Okay, yes. Then we write this step. Okay, we write f of s. How I'm going to write f of s, capital F of s? See it here. Okay, so f of s can be written as, okay, 1 upon s. Okay, and that 2, that means 2 under bracket, this entire term gives us a sine s. Okay, sine s, and that s it is a denominator here. Okay, so this one is our required Fourier transform. Okay, so we evaluate the integral. Okay, we evaluate the piecewise integral 1 and 0, and I found the Fourier transformation 2 times sine s upon s. Okay, I hope you all have understood my entire Fourier transformation. It is not the difficult, guys, one of the easy solution here. For your reference, you can see this my entire solution. Okay, yes, but still we have half part of our solution it is remaining. Okay, so we go for finding the value for integral over 0 to infinity sine x upon x dx. Okay, let's get start this solution. In our next part, what we have to do, we have to find out the value for 0 to infinity sine x upon x dx. Okay, what we have to find out, we have to find out the value for 0 to infinity sine x upon x dx. Okay, so for this we have to apply inverse Fourier transformation. Okay, yes, as you have to evaluate this integral, we know that this sine x upon x is in the form of Fourier transformation. We found the answer. Okay, yes, so you have to evaluate this integration, means you have to take inverse of a Fourier transformation. Okay, that means we have to apply inverse Fourier transformation. Okay, and we know that inverse Fourier transformation can be written as f of x, which is equal to 1 upon 2 pi minus infinity to infinity capital F of s e raised to minus isx dx. Okay, yeah, this one is a ds. So this one is a capital F of s. Okay, this one is a Fourier transformation. So we have to replace the value Fourier transformation F of s here. Okay, so we'll go for the replacement of the values here. So here in our next step, I replace the value for f of x as 1 upon 2 pi as it is here, minus infinity to infinity as it is 2 times. This one is our given Fourier transformation f of s that we found it earlier. Okay, and the e raised to minus is x ds as it is. Okay, yes. So we want the value for integral 0 to infinity sin x upon x dx. Okay, so for that we are going to solve this integral here. Okay, so 1 upon 2 pi. Okay, keep 1 upon 2 pi as it is, as I'm not going to do any changes right now here. Okay, yes. So 1 upon 2 pi into 2. So 2 also take it outside 2, and integration minus infinity to infinity sin s upon s e raised to minus I s x dx ds. Okay, e raised to minus I s x ds. Okay, these are the replaced value. Now we can see that we can cancel 2 with the 2. Okay, so minus infinity to infinity sin s upon s e raised to minus I s x dx, which is the value for f of x we have here. Okay, so this one is the f of x we found here. Okay, so minus infinity to infinity sin s upon s. So we have to find out the value for this integral. Okay, as it is like we have to apply some of the concept from even function, odd function is it in. Okay, for solving further integral. Okay, so we have challenging part, it is only here. Okay, so for solving this integral further, we need to apply some even odd concept. Okay, concept of even function, concept of odd function. Okay, as we know that sin s, it is an odd function. How it is an odd function already I explained in my previous lecture, but still I'm going to explain it here. Okay, so f of x, f of s we have here is a sin s. Okay, odd function, what it says that whenever we have f of minus x, okay, whenever we have f of minus x, which gives us a minus of f of x. Okay, if this condition hold, then we say that it is an odd function. Okay, yes. So f of s, which is equal to sin s. Okay, so f of minus s, let me write f of minus s, which is the sine of minus s. Okay, f of minus s can be written as sine of minus s. Okay, and a sine of minus theta, as we all know that minus sine theta. Okay, minus sine s. So f of minus s, I got the minus sine s here. Okay, yes. So f of s is a sine s, then f of minus of f of s I'm going to write as a minus of sine s. Okay, I multiplied negative to the both side. Now see that minus sine s, if these are equal, then we write f of minus s, which is equal to minus of f of s. Okay, yes. So if f of minus of x is equal to minus of f of x, it is there now, then we say that sine s. Okay, sine s is a odd function. Okay, odd function. It satisfies definition for odd function. Now obviously it is odd function, and similarly we know that s is also odd function. How s is also odd function? Okay, you have to find. It is not given whether it is odd or even. You just have to find it out. It is odd or not. Okay, so how s is odd function? Let me explain here. Okay, so f of s, which is equal to s. Okay, yes. So f of minus s, it become minus s. Okay, so f of minus s gives us the minus s value, then f of minus s is equal to minus of f of s. Okay, so replace s as a f of s. So f of minus s as a minus sign, keep as it is. S instead of s, replace f of s. Okay, s means this s is equal to f of s. So f of minus s is equal to minus of f of s. So we write s is also odd function, sin s is odd function, s is also odd function. We can see here then odd function upon odd function. We know that odd function upon odd function, we know that odd function upon odd function is a even function. Okay, odd function upon odd function is a even function. And we know one more result. Whenever we have minus infinity to infinity sin x upon x dx. Okay, and this is a even function. Okay, if this one is a even function, okay, what we do, whenever we have integration minus infinity to infinity sin x upon x dx, it is a even function. Okay, so if it is a even function, then we write the value for this entire term is the pi. Okay, this entire term we write the pi. Only it happen when this term is the entire term. Odd upon odd means it need to be a even. Okay, yes. So let me solve this step further here. Okay, yes. So f of x, which is equal to 1 upon pi, 2 cancelled here, minus infinity to infinity, sin s upon s, e raised to minus is x ds. Okay, now see that as we don't have the integration in the form of x, it is in the integration is in the form of s, so we can replace the value for x. Why we have to replace? Because we need to find out the value for f of x. Okay, what we need here, we have to find out the value for f of x. That's why I'm going to replace that x here. Okay, and replace the value where you can get the easy function. Okay, yes, so I'm going to replace x as a 0 in this step. Okay, replace here x as a 0. In this step I have to replace x which is equal to 0. I'm going to replace x 0 here. Okay, yes, so f of 0 can be written as 1 upon pi. Okay, f of 0 can be written as 1 upon pi. Okay, minus infinity to plus infinity. Okay, sin s upon s. Okay, sin s upon s. Now see that e raised to minus I times s times 0 ds. Okay, so e raised to 0 multiplied by this step. Okay, that means it entire step goes to 0. That means e raised to 0, it gives us the value 1. Okay, now see that we left here the value minus infinity to infinity. Okay, so take pi, it is to the other side. Okay, now we want the value for f of 0 also. Okay, now let me explain how can we find the value for f of 0. It is one of the easier, guys. Okay, not that difficult. Let me explain here. So see here, I want the value for f of 0 now. Now see that whenever we have value for x which is a 0, now see that f of 0 means x is a 0. Okay, f of 0 means x is a 0. So if I consider that x is a 0 here, okay, x is a 0, replace x is a 0, then we get the f of 0 here. Okay, so I'm taking from this interval as a 0. Okay, as we want the value for f of 0. So if x is a 0, then means we write f of 0, and then f of 0 can we write 1? Yeah, obviously we can write, because this is the value which come to this function, which come to this piecewise function. So whenever x is a 0, we write f of x is 1. Okay, whenever x is a 0, we write f of x is 1. That means f of 0 is a 1 over here. Okay, I hope you all have understood how f of 0 gives us the value 1. Okay, so replace only x as a 0. So f of 0 which is equal to 1. So we write f of 0 is a 1 here. Okay, and 1 upon pi denominator here take to the other side. So we write 1 multiplied by pi. Okay, so 1 multiplied by pi. Okay, integration minus infinity to infinity. Okay, sin s upon s, e raised to minus infinity to infinity, sin s upon s ds. Okay, yes, now see that here. So in our next step, we know that we are going to apply one more result here. Okay, this one is the result. Consider this one, minus infinity to infinity f of x dx can be written as 0 to infinity f of x, 2 times 0 to infinity f of x dx only. Okay, only it is the even function. Okay, this one is the result. I am going to apply it here. Okay, now see that pi it remain as it is. Okay, 2 times 0 to infinity sin s upon s ds. Okay, take 2 here, so we write pi by 2, 0 to infinity. Okay, sin pi by 2, 0 to infinity sin s upon s ds. Okay, so now see that what we want in our given integral, sin s upon s ds 0 to infinity, but this one is not fully correct answer. Okay, so actually answer it is coming right here. Okay, answer it is coming right, but it is not fully correct, as we have the interval minus infinity to infinity defined on our sin s. Okay, yes, so for that what we do, we are trying to make this interval into the finite interval. Okay, so as it is an infinite interval now, that's why it gives us the partially correct answer. So I want the fully correct answer. So for this what we do, we are trying to convert that negative terms, okay, that negative infinite terms into the some positive finite integral. Okay, now see that for that I am going to apply limit, some of the concept from the limit here. Okay, so that limit we apply here only this to this step. Okay, only to this step. Yes, so I'm going to apply a limit to this step only. So for after this, I'm going to explain to you all only after this. Okay, yes. So remember this step. For that step you are going to solve, because we are not going to take this step as these are the answer partially correct, because it is defined on infinite interval. So we cannot say specific fixed value, it is a pi by 2. Okay, but now we are going to take it to the some of the concept from the limit. Okay, so let's go for after this step. Okay, pi, which is equal to minus infinity to infinity sin s upon s ds. So see guys very carefully, okay, how I'm going to solve. Okay, as we know that minus infinity to infinity sin s upon s ds, it is a equal to pi. This one is our last step. Okay, so as we directly cannot apply infinite integration, so what we do, we are trying to make it is the finite. Okay, finite one. So for making finite one, we apply limit as a tends to infinity. Okay, we apply limit. Apply limit. How I am going to apply limit now? See here, limit as a tends to infinity. Okay, a goes to the infinity minus a to a. Now see that if we replace a as a infinity, we write minus infinity here. Again we replace a as infinity, we write infinity here. Okay, so be careful with the substitution of the limit. Okay, so I taken limit a tends to infinity outside, minus a to a here. Okay, in order to make this integration finite. Okay, so sin s upon s ds. Okay, yes, which is equal to pi. I hope you all have understood what I have done. Instead of minus infinity, I written as minus a, and infinity I written as a. Remaining term as it is, and I at the out of integral I written here a goes to the infinity. Okay, this is the standard rule for solving integration integral. Okay, for infinite terms. Yes, now we know that minus infinity to minus some value to some plus value. Okay, sin s upon s. Okay, sin s upon s, we write to 2 times 0 to a. Okay, 2 times 0 to a, this one is our standard result. Okay, yes, whenever we have even function. Okay, whenever we have even function, we write minus a to a f of x dx as a 0 to a. Okay, 0 to a, 2 times 0 to a f of x dx. This one is the rule for integration we are going to apply here. Okay, only when function is a even. Okay, only when function is a even. So we know that odd sin s is odd function, s is odd function, odd upon odd, it is even function. Okay, so in this even function, what we are going to do, we are going to replace this step here. Okay, so keep limit a tends to infinity as it is, limit as a tends to infinity. Okay, so I kept that limit a tends to infinity as it is here, minus a to a. That means minus a to a f of x dx can be written as 2 times 0 to a, 2 times 0 to a sin s upon s ds, which is equal to 5. Okay, yes, I hope you all have understood my next step, how I have written. Okay, so pi I kept as it is, ds it is also as it is, sin s upon s also as it is. Okay, so minus a to a f of x dx, okay, can be written as 2 times 0 to a f of x dx. Okay, I replace these values here. Yes, I hope you all have understood. Now directly you can replace the value as infinity. So we are going to write 2 times 0 to infinity. Okay, sin s upon s ds, which is equal to pi. Okay, yes, 2 times 0 to infinity sin s upon s ds, which is equal to pi. So take the 2 to the other side, 0 to infinity sin s upon s ds, which is equal to pi divided by 2. Okay, this one is our required integral that we have to find. Okay, that it is our the question. Okay, so we want the value for integral 0 to infinity sin of s upon s ds, which is equal to pi by 2. Okay, now see that this one is our integral. We want the value for 0 to infinity sin s upon s ds. Okay, yes, but as we want in the term of x. Okay, so we have given, it is in the question, sin x upon x, but we have sin s upon s, and we know the one more standard result for integration, we can replace s by some another variable. So 0 to infinity sin x upon x dx, which is equal to pi by 2. Okay, this one is our required answer. Okay, so see that guys, how easy solution it is. So these questions, okay, asked in a SPPU question paper many more times. I hope you all have understood how to find out the Fourier integral using Fourier transformation, formula for Fourier transformation. Thereafter we found the value for integration 0 to infinity sin x upon x dx using inverse Fourier transformation. Okay, that's it here for my today's lecture, guys. I hope you all have understood everything here in my today's lecture. Even after, if you found anything difficult, let me know in my comment section. I will come up with the similar videos. So thank you everyone. Thank you for my today's lecture.